Okay, hi everyone. Let's have our last topic for this week, which is the use of thermodynamic property relations in specific cases. Okay, so one specific case that we could consider are for two-phase systems. Okay, so for two-phase systems, consider one mole of species undergoing phase transition, and let's consider the Gibbs free energy of phase transition. Okay, so using from the definition of Gibbs energy from the fundamental property relation, dG is equal to VdP minus SdT. However, we know that phase transition occurs at constant temperature and at constant pressure. So kung constant T and constant P ang ating phase transition, this simply means that for any phase transition process or for any pure phase change, dG is just equal to 0. Okay? Or delta G is equal to 0. So delta G of vaporization, delta G of fusion, and so on is just equal to 0. So therefore, for any two phases na let's call these phases alpha and beta, okay, so G alpha is equal to G beta or dG alpha is equal to dG beta. Okay, so from this, di ba, meron tayong dG alpha is equal to dG beta. Okay, so from here, we can write the fundamental property relation for the alpha species and the beta species. Okay, so dG is equal to VdP minus SdT again. Okay, so for the alpha phase and the beta phase. Okay, and from here, okay, nakapisat tayo kasi ito yung saturation pressure. Okay, at this particular phase change process. Okay, so if you rearrange this, okay, you can get the following expression where dP sat over dt, okay, is equal to S beta minus S alpha, which is just equal to delta S alpha beta divided by V times beta minus V alpha, which is just delta V from alpha to beta phase. Okay, and from here, we can use the fundamental property relation or the definition of delta G. Okay, so delta G is equal to delta H minus T delta S. And for a phase transition, this is equal to 0. And we can replace this delta S, okay, by delta H alpha beta all over T. So replacing this, okay, you can now arrive at this expression, which should be familiar, and this is known as our Clapeyron equation. So I'm not sure if this was discussed to you in your chemistry, pero ito yung derivation of the Clapeyron equation, okay, for general phase change processes. Okay, now for vapor liquid systems, so vaporization processes, we can replace alpha and beta by delta H LV, so delta H of vaporization all over T times delta V of vaporization. Okay, now we can obtain an expression, okay, for delta V LV from the compressibility factor, where Z is equal to PV over RT, and therefore delta Z from alpha to beta is equal to, so delta Z is equal to P over RT delta V LV. Okay, so changing this, so delta Z LV is equal to P over RT times delta V LV. Replacing this expression, okay, in here, and you can get the following expression. So si T, pwede nating ilipat dito. Okay, so D1 over T. Yan, so DL and P sat all divided by D1 over T is equal to delta H LV, negative delta H LV all over R delta Z LV. Okay, now, to make some assumptions, for an ideal gas, Z should be equal to 1, or okay, and for liquid, Z should approach 0, meaning delta ZLV is just equal to 1. So therefore, DL and P sat of divided by D1 over T is equal to negative delta H of vaporization over R, and this is known as our Clausius-Clapeyron equation. Okay, so this equation gives us the temperature dependence of our um, heat vaporization, okay, as a function of pressure, saturation pressure, and temperature. Okay, so from here, the Clapeyron equation actually provides us a vital connection between the properties of different phases. And the Clapeyron equation is an exact differential equation. However, we need to know a relationship between temperature and saturation pressure, and typically these relationships are empirical in nature. Okay, so for the Clapeyron equation, kailangan natin ng T as a function of Psat. Okay, and we have multiple empirical relations for this. So you have a linear relationship between ln Psat and temperature, okay, which is similar to our Antoine equation. And you also have others like your Wagner equation here. And of course, you also have our reduced temperature dependency of PRSat and TR. Okay, so yeah, for the Kessler correlation, okay, for saturation pressure as a function of the reduced temperature. Okay, so last but not least naman, let us examine the actual behavior of throttling processes for real fluids. Okay. So again, recall for a throttling process, this occurs when a fluid passes through a restriction, such as a porous plug, capillary tube, or an ordinary valve, where the pressure simply decreases. Okay, so consider now na meron tayong fluid at 20 degrees Celsius and at pressure 800 kPa, then flows through this valve. So we're reducing pressure to 200 kPa. Now the question is, what will happen to the temperature of the fluid downstream? Kasi for an ideal gas, alam natin na throttling process, delta H is equal to 0, enthalpy is only a function of temperature for an ideal gas. So therefore, kung ideal gas, dapat T2 is equal to T1. Pero for real gases, the behavior may be different. Okay, so the temperature may decrease or the temperature may increase now. And the temperature behavior of the fluid throughout the throttling process is now described by your Joule-Thomson coefficient. And the thermodynamic definition of the Joule-Thomson coefficient is the change in temperature with respect to pressure at constant enthalpy. Kasi throttling processes are at constant enthalpy. Okay. So now, how do we determine the values of the Joule-Thomson coefficient? Okay, so to determine the value of the Joule-Thomson coefficient, okay, so mag-start tayo lagi at a fixed temperature and pressure, okay, and in the conditions, and i-vary natin ngayon yung opening ng restriction. So you vary the opening restriction sa valve to vary the downstream pressure. Okay? And when you vary downstream pressure, re-record mo ngayon yung temperature. So you will do this for multiple pressures and multiple downstream pressures to obtain now a constant enthalpy line. And this constant enthalpy line, okay, so starting from 1, so first run mo from 1 to this particular pressure. Okay? So, lagi tayong decreasing pressure. Lagi to the left yung pressure natin. Decreasing siya kasi throttling process. Okay? So, start ka from 1 to 2 dito. Tapos, start ulit from 1. Tapos to another pressure and so on until you obtain this line. And you can do this for multiple starting points of the temperature and multiple starting points for the pressure. Okay? So, to obtain this line. And mapansin natin ngayon, sa line na to, magkakaroon tayo ng change in slope. May part ng line may part ng curves na negative ang slope natin, may part ng curve na positive ang ating slope. Okay, so ano yung significance ng mga to ngayon? Okay, recall that the Joule-Thomson coefficient now is defined as JT is equal to change in temperature with respect to pressure holding enthalpy constant. And yung mga lines natin na yan, these are known as our constant enthalpy lines. Okay, at meron tayo ngayong change in the derivative here. Okay, so with this, the slope of the line at each point represents the value of the Joule-Thomson coefficient. So, meron tayo dito na tawag na inversion point. And the inversion point signifies kung saan nag-change yung sign ng ating Joule-Thomson coefficient. Okay, so if the Joule dito sa right-hand side, okay, negative ang ating Joule-Thomson coefficient. At sa left-hand side, positive ang ating Joule-Thomson coefficient. Okay, so anong sinisignify nito ngayon? Kung mag-increase ba yung temperature or magdi-decrease yung temperature as you proceed with the throttling process. Okay? So, The Joule-Thomson coefficient now provides us the measure of change in the temperature with respect to pressure in a throttling process. Okay? So again, the slope in the constant enthalpy line gives us the value of the Joule-Thomson coefficient. Now recall, dP in a throttling process is always negative. Okay? Kasi lagi tayong nagde-decrease ng pressure. So pag ganito, if the Joule-Thomson coefficient now is positive, okay, this means dt is negative. So if the Joule-Thomson coefficient is positive, therefore the change in temperature is negative. If the Joule-Thomson coefficient is negative, this means the change in temperature is positive. Okay? So pag Joule-Thomson coefficient negative, mag-increase yung temperature as you go down the throttling process. Okay? However, if the Joule-Thomson coefficient is zero, wala tayong change in temperature. So that's one way for you to determine kung mag-increase or decrease yung temperature using the Joule-Thomson coefficient. However, okay, if you take a look at this plot, so from A, okay, A to B, okay, ang Joule-Thomson coefficient natin is negative. Okay, so pag negative Joule-Thomson coefficient, therefore, mag-increase yung temperature. And as you can see, pumabot ka sa point B, nag-increase yung temperature. Okay, pero pag A to C naman, mag-increase pa rin yung temperature kahit meron kang change in sign. Kasi ang starting point mo dito sa right-hand side ng inversion point. Okay, so we call point B the inversion point. So meron tayong inversion temperature and inversion pressure. Pero kung mag-start ka naman dito sa point B to the left of point B, okay, negative all throughout ng at Joule-Thomson coefficient. Sorry, positive all throughout dito ang Joule-Thomson coefficient. So therefore, magiging lagi tayong magde-decrease ng temperature. Okay? Okay, so now let us try to prove for an ideal gas that the temperature remains constant for a throttling process. So for this, let us use the function of enthalpy in terms of temperature and pressure, which have previously derived. Okay, and recall for a throttling process, this is equal to 0 kasi dH is equal to 0. So now Cp dt is equal to negative of negative T partial of V with respect to T at constant P plus V times dP. Okay? Now, kailangan natin ngayon ng expression, okay, for the Joule-Thomson coefficient. And the Joule-Thomson coefficient again is equal to the change in temperature with respect to pressure at constant enthalpy. Okay? So para gawin yan, pwede natin ilipat si Cp sa kabila and divide both sides by dP, holding enthalpy constant. Okay, so doing this, okay, you can get this expression now. Okay, so dt over dP at constant H is equal to the following expression. Mawawala na si dP, so makakancel na siya with divide natin by dP. Okay, so evaluate na natin to for an ideal gas. And again, ideal gas, V is equal to RT over P. So therefore, partial of V with respect to T at constant P is just equal to R over P. Okay. So this is now equal to R over P times T, and this whole term is equal to negative V. So negative V plus V, this whole term is equal to 0. So therefore, the partial of T with respect to P at constant H is equal to 0, which is equal to the Joule-Thomson coefficient for any ideal gas. So therefore, for any throttling process ng ideal gas, the Joule-Thomson coefficient is always equal to 0. Therefore, the temperature will remain constant. So mathematically, it now holds true na for a throttling process, constant enthalpy, and the enthalpy of an ideal gas is equal to 0. Ideal gas only dependent on the temperature rather, and delta H is equal to 0, therefore delta T or dt should also be equal to 0. And we have proven this again using this mathematical relation for H as a function of T and P and the Joule-Thomson and its relationship with the Joule-Thomson coefficient. And that's it for our discussion on these specific cases for thermodynamic property relations. Okay, this is now our penultimate topic for ChemE 122. And our last topic now for ChemE 122 will be the derivation of the real properties of fluids. Okay, so ano na yung mga real enthalpy changes and real entropy changes for non-ideal gases. So that's it, and thank you for listening.